Hey there, how was your day? I hope wherever you are in this vast cosmos, you found a moment of peace to join me on this incredible journey we're about to take together. Tonight, we're going to explore a question so immense, so quietly overwhelming, that it has the power to completely reshape how you see your place in existence itself. How big is the observable universe? The visuals are here for you, but there's absolutely no problem if you drift off midway through. Feel free to close your eyes, breathe deep, and let your imagination expand at the speed of wonder itself. Sometimes the most profound truths are best absorbed when we allow our minds to float freely through the cosmic dark. Let's start now.
Imagine for a moment that you're standing in your backyard on a clear night, looking up at the stars. Each pinprick of light represents a sun, many of them far more massive and brilliant than our own. But here's what will absolutely transform how you see that view forever.
Every single star you can see with your naked eye, every constellation that has guided human navigation for millennia, every celestial landmark that has inspired countless generations of dreamers and poets, represents less than 1/10 billionth of what actually exists in the observable universe. Let that sink in for a moment. Everything your eyes can take in during a lifetime of stargazing is such an infinitely small fraction of reality that it's almost mathematically insignificant. And yet, even this incomprehensibly vast observable universe might itself be just a tiny bubble floating in something even more enormous than we can possibly conceive. Welcome to a journey that will take us from the familiar boundaries of our solar neighborhood to the very edge of everything we can theoretically observe. We'll discover why there's a limit to how far we can see, not because our telescopes aren't powerful enough, but because of the fundamental nature of space, time, and light itself. We'll explore how the universe's own expansion creates a cosmic horizon beyond which no information can ever reach us, no matter how long we wait or how advanced our technology becomes. But first, let's establish something that might surprise you. When astronomers talk about the observable universe, they're not talking about everything that exists, they're talking about everything we could possibly see, even with perfect instruments and unlimited time. The distinction is crucial because it reveals one of the most profound limitations built into the very fabric of reality itself. The observable universe has a radius of approximately 46.12 billion light-years in every direction from Earth. That means it's a sphere roughly 93 billion light-years across, containing everything from which light has had enough time to reach us since the beginning of time itself. But here's where it gets fascinating and slightly mind-bending. The universe is only about 13.8 billion years old. So how can we see objects that are 46 billion light-years away? The answer lies in one of the most elegant and mysterious features of our cosmos. Space itself is expanding. While light from distant galaxies has been traveling toward us for billions of years, those galaxies have been carried farther and farther away by the expansion of space itself. It's like watching a runner on a treadmill that's moving backward faster than they can run forward. The light eventually reaches us, but by the time it arrives, its source is much, much farther away than when the journey began. This creates something called the particle horizon, the boundary of our observable universe. Beyond this horizon lies what we might call the unobservable universe, regions of space that exist but remain forever hidden from our view. No telescope will ever peer beyond this boundary. No signal will ever cross it. No information will ever bridge this cosmic divide. It's not a limitation of technology or human ingenuity. It's a fundamental feature of reality itself, written into the laws of physics that govern everything. But let's start our journey small and work our way outward, building our cosmic perspective one scale at a time. Because understanding the true size of the observable universe requires us to first grasp just how empty and vast space is, even in our own celestial neighborhood. Picture Earth as a marble sitting on a football field. On this scale, the moon would be a peppercorn about 7.5 yards away. Already, the distance has become difficult to visualize, but we're just getting started. The sun, our local star that seems so dominant in our sky, would be a beach ball sitting about 2.5 miles away from our marble Earth. And the nearest star beyond the sun, it would be another beach ball located roughly 13,000 miles away. This is the scale of just our immediate stellar neighborhood, and already We're dealing with distances that challenge human comprehension. But this is nothing compared to what lies ahead. Our entire solar system, including the distant orbit of Neptune and the scattered objects of the Kuiper Belt, would fit within a circle about 10 miles across on our football field scale. But our galaxy, the Milky Way, contains roughly 400 billion stars, each separated by these mind-numbing distances. If our solar system is 10 miles across, then our galaxy would span the entire continental United States. And this is just one galaxy among countless others scattered throughout the observable universe. The Milky Way belongs to a small group of galaxies called the Local Group, which includes our neighbor Andromeda, a few dozen smaller galaxies, and a handful of dwarf companions. This entire local group spans about 10 million light-years across, but even this collection of galaxies is just a tiny cluster in a much larger structure. The local group is part of something called the Virgo supercluster, a vast collection of galaxy groups and clusters that spans roughly 110 million light-years across and contains thousands of galaxies. When you look up at the night sky, every star you see belongs to our single galaxy, but our galaxy is just one of thousands in this local supercluster. But we're still not even close to grasping the full scale of what we can observe. The Virgo supercluster is itself part of an even larger structure called the Laniakea supercluster, which contains roughly 100,000 galaxies spread across 520 million light-years. The name Laniakea comes from Hawaiian words meaning immeasurable heaven, and it's a fitting description for a structure so vast that light takes over 500 million years to cross it. And yet, Laniakea is just one of millions of similar superclusters scattered throughout the observable universe like islands in an infinite cosmic ocean. Between these superclusters lie vast regions of nearly empty space called cosmic voids. These voids are so large that entire superclusters could fit inside them with room to spare. Some voids are over 1 billion light-years across, containing almost nothing but the occasional lonely galaxy drifting through the cosmic darkness. This creates what cosmologists call the cosmic web, a stunning large-scale structure where matter is arranged in filaments and sheets separated by enormous voids. If you could somehow step outside the observable universe and look at it from a distance, it would resemble a vast three-dimensional spiderweb with bright filaments of galaxies separated by dark empty spaces. The cosmic web stretches across the entire observable universe, and every galaxy, every star, every planet, every living thing exists somewhere within this magnificent structure. We are part of this web, tiny inhabitants of a small planet orbiting an ordinary star in an unremarkable galaxy that sits along one of these cosmic filaments. But here's what makes this truly extraordinary. The cosmic web isn't random. Its structure was determined by tiny quantum fluctuations that existed when the universe was smaller than an atom. These microscopic variations in density grew over billions of years, shaped by gravity and the expansion of space itself, until they became the vast architecture we observe today. Every galaxy cluster, every void, every filament in the cosmic web can trace its origins back to quantum uncertainties that existed in the first fraction of a second after the Big Bang. The universe has grown from quantum foam to cosmic web, from the smallest possible scales to the largest structures we can observe. And as we map more and more of the observable universe, we discover that this cosmic web extends as far as we can see in every direction. No matter which way we point our telescopes, we find more galaxies, more clusters, more superclusters arranged in the same web-like pattern. The observable universe appears to be filled with structure on every scale we can measure. But there's something even more remarkable about the cosmic web that speaks to the fundamental nature of reality itself. The visible matter that makes up galaxies and stars accounts for less than 5% of everything in the observable universe. The rest is composed of mysterious substances we call dark matter and dark energy, invisible components that reveal themselves only through their gravitational effects on the matter we can see. Dark matter makes up about 27% of the observable universe. It doesn't emit, absorb, or reflect light, but its gravity shapes the cosmic web, providing the scaffolding around which visible matter clusters. Without dark matter, galaxies couldn't have formed, stars couldn't have ignited, and the cosmic web itself couldn't exist. Dark energy comprises the remaining 68% of everything, and it's even more mysterious. This invisible force is driving the accelerating expansion of space itself, pushing galaxies apart and stretching the cosmic web ever larger. Dark energy is why distant galaxies are receding from us faster and faster, and why the observable universe has a finite size despite the universe's ongoing expansion. This means that the vast majority of the observable universe consists of things we cannot see, touch, or directly detect. We are like explorers mapping an invisible continent, inferring the presence of mountains and valleys only by watching how rivers flow around them. The cosmic web we observe is merely the visible tip of a much larger hidden architecture that shapes everything around us. But even these staggering scales pale in comparison to what we discover when we consider the observable universe as a whole. Recent measurements suggest that the observable universe contains at least 2 trillion galaxies, each containing hundreds of billions of stars. That's more stars than there are grains of sand on every beach on Earth, multiplied by every beach that has ever existed throughout our planet's history. Let me put this in perspective for you. If you counted 1 star every second without stopping, it would take you longer than the current age of the universe to count all the stars in just one large galaxy. To count all the stars in the observable universe at this rate would require more time than has elapsed since the Big Bang, multiplied by trillions upon trillions. And yet, despite containing this incomprehensible number of stars and galaxies, the observable universe remains mostly empty space. If we distributed all the matter in the observable universe evenly throughout its volume, we would end up with roughly 6 protons per cubic meter. That's emptier than the best vacuum we can create in laboratories on Earth. This emptiness isn't a flaw in cosmic design, it's a fundamental feature that makes complexity possible. Without vast spaces between stars, planetary orbits would be unstable. Without enormous distances between galaxies, gravitational interactions would prevent the stable structures necessary for life. The universe's emptiness is what allows islands of matter to exist as oases of complexity in an ocean of space. As we push our observations to greater and greater distances, we're not just looking farther into space, we're looking backward through time itself. Light travels at a finite speed, roughly 300 million meters per second, which means that distant objects appear to us as they were when their light began its journey to Earth. When we observe a galaxy 1 billion light-years away, we're seeing it as it existed 1 billion years ago. The light carrying that image has been traveling through space for 1 billion years, crossing vast distances while the universe itself expanded around it. By the time that ancient light reaches our telescopes, the galaxy that emitted it may have evolved, changed, or even been destroyed by cosmic forces we cannot yet observe. This creates a remarkable consequence. As we peer deeper into space, we're witnessing the universe's history unfolding before us. The most distant galaxies we can observe appear young, chaotic, and fundamentally different from the mature spiral and elliptical galaxies we see nearby. We're watching cosmic evolution in reverse, seeing the universe grow younger and more primordial as we look farther away. The most distant objects we can currently observe are galaxies that formed when the universe was less than 1 billion years old. These ancient systems appear as small, irregular collections of stars, frantically forming new suns at rates hundreds of times faster than galaxies today. They give us glimpses of the cosmic dawn, when the first stellar nurseries were igniting throughout the expanding universe. But even these incredibly distant galaxies aren't the farthest things we can observe. The most distant light we can detect comes from the cosmic microwave background, radiation left over from when the universe first became transparent, roughly 380,000 years after the Big Bang. This ancient light fills the entire sky with a faint glow that's invisible to our eyes, but detectable by sensitive radio telescopes. It represents the afterglow of creation itself, the moment when the universe cooled enough for the first atoms to form and light to travel freely through space for the first time. The cosmic microwave background marks the edge of our observable universe, not because nothing exists beyond it, but because we cannot see anything that happened before the universe became transparent. It's like trying to peer through fog so thick that no light can penetrate. The cosmic microwave background is our cosmic fog, the fundamental limit to how far back in time we can observe. This creates one of the most profound realizations about the observable universe. We live at the center of our observable sphere, not because we occupy a special place in the cosmos, but because we can only see objects from which light has had time to reach us. Every observer in the universe sits at the center of their own observable sphere, each with a slightly different view of cosmic history.
An observer in a galaxy 10 billion light-years away would see their own observable universe overlapping with ours, but extending in directions we can never explore.
They might observe galaxies that remain forever hidden from our view, while some of the galaxies we can see lie beyond their cosmic horizon. This raises a fascinating question about the nature of existence itself. If there are regions of the universe that can never send us information, that we can never observe or influence, do they truly exist in any meaningful sense? Or does existence require the possibility of observation and interaction? Modern physics suggests that these unobservable regions are indeed real, filled with galaxies, stars, and possibly even civilizations that are simply too far away for their light to reach us. The universe beyond our cosmic horizon continues the same cosmic web, the same processes of stellar birth and death, the same dance of matter and energy that we observe within our visible sphere. But we can never confirm this directly. The unobservable universe remains forever theoretical, inferred from our understanding of cosmic uniformity and the laws of physics, but never directly witnessed. It exists in a realm beyond empirical science, where mathematics and philosophy converge to grapple with questions of existence and reality. The expansion of space itself ensures that our observable universe is constantly changing. Every second, light from more distant regions crosses our cosmic horizon and becomes observable for the first time. We are constantly receiving new information from the early universe, watching the cosmic story unfold as ancient light finally completes its billion-year journey to our telescopes. But paradoxically, the accelerating expansion driven by dark energy means that many galaxies we can currently observe are moving away from us so rapidly that we will eventually lose sight of them. Their light will become so stretched by cosmic expansion that it fades beyond detection. Future astronomers will inhabit a lonelier universe, with fewer visible galaxies and less evidence of cosmic history. In the far future, if current theories are correct, the observable universe will contain only our local group of galaxies. The rest of the cosmic web will have expanded beyond our horizon, leaving future civilizations with no way to discover the Big Bang, cosmic expansion, or the rich tapestry of cosmic evolution that we are privileged to observe today. This temporal window makes our current era special in cosmic history. We live at a unique moment when the universe is old enough for complex structures to have formed, but young enough that we can still observe the evidence of cosmic origins. We are cosmic archaeologists, working within a limited time frame, racing to understand our origins before the expanding universe erases the evidence. The observable universe thus represents not just a spatial boundary, but a temporal one as well. It defines not only how far we can see, but how much cosmic history remains accessible to scientific investigation. Every observation we make, every discovery we achieve, adds another piece to a cosmic puzzle that becomes more difficult to solve with each passing billion years. As we contemplate these vast scales, something profound begins to emerge about our place in this cosmic theatre. The observable universe isn't just a collection of distant objects scattered through space. It's a living, breathing entity that connects us to every other point of light in the cosmic web, through the fundamental forces that govern reality itself. Consider this remarkable fact. Every atom in your body was forged in the nuclear furnaces of ancient stars that lived and died billions of years before our solar system even existed. The calcium in your bones, the iron in your blood, the oxygen you breathe at this very moment. All of these elements were created in stellar cores and scattered across the cosmos by supernovae that lit up galaxies when the universe was young. You are not separate from the observable universe. You are made of it. You are the cosmos, becoming aware of itself, a temporary arrangement of stellar debris that has somehow achieved the extraordinary feat of consciousness. Through your eyes, the universe observes its own immensity. Through your mind, it contemplates its own origins and destiny. This connection runs deeper than mere poetic metaphor. The laws of physics that govern the behavior of galaxies billions of light years away are the same laws that govern the electrical impulses in your brain. As you process these words, the gravitational forces that hold galaxy clusters together operate on the same principles that keep your feet planted on the ground. The electromagnetic radiation that carries information across cosmic distances is the same force that allows your neurons to communicate with each other. But here's where the scale of the observable universe becomes truly mind-altering. If we could somehow shrink the entire observable universe down to the size of Earth, our own galaxy would be smaller than a single cell in your body. Our solar system would be invisible to the most powerful microscopes, and Earth itself would be so inconceivably tiny that it would exist on scales smaller than we have words to describe. Yet, on this infinite decimal speck, in a universe so vast that our entire galaxy is essentially a point, complexity has reached levels that boggle the mind. Life has emerged from lifeless matter. Consciousness has arisen from unconscious atoms. Intelligence has developed to the point where it can contemplate its own cosmic context and ask questions about the nature of existence itself. This creates one of the most beautiful paradoxes in all of cosmology. We are simultaneously insignificant and extraordinary. Insignificant because we occupy such an infinitesimally small portion of space and time. Extraordinary because, despite our cosmic smallness, we have managed to map the observable universe, understand its history, and predict its future. The observable universe reveals itself to us through light, that fundamental messenger that connects every corner of cosmic space. But light does more than just carry information. It defines the very structure of space-time itself, creating the boundaries of what we can observe and establishing the cosmic horizons that limit our knowledge. Einstein showed us that space and time are woven together into a single fabric, and the speed of light represents the maximum rate at which information can travel through this cosmic tapestry. This speed limit isn't just a property of light itself, it's a fundamental feature of reality that governs how cause and effect propagate through the universe. Every photon that reaches your eye from a distant star has been traveling at exactly this cosmic speed limit for years, decades, centuries, or even billions of years. These ancient messengers carry with them the history of their journey, encoded in wavelength that tell us about the temperature, composition, and motion of objects scattered throughout the observable universe. When astronomers analyze the light from distant galaxies, they're not just seeing pretty pictures, they're decoding messages that have traveled across unimaginable distances, carrying information about stellar births and deaths, the formation of heavy elements, the merger of galaxies, and the evolution of cosmic structure itself. The existence of dark energy means that we live during a special epoch in cosmic history. We inhabit a universe old enough for complex structures to have formed, but young enough that we can still observe evidence of cosmic origins and evolution. Future civilizations will face a lonelier cosmos, with fewer visible galaxies and less accessible information about cosmic history. This temporal window makes every observation precious, every measurement valuable. We are cosmic archaeologists, working within a limited time frame, racing to understand the universe before the expanding cosmos erases the evidence. Each photon we collect from distant galaxies represents irreplaceable information about cosmic evolution, stellar formation, and the fundamental forces that shape reality. The observable universe thus serves as both our laboratory and our library, containing within its boundaries all the information we can ever hope to gather about the nature of existence itself. Every star we observe, every galaxy we catalogue, every measurement we make, adds another piece to the grand puzzle of cosmic understanding. But perhaps most remarkably, the observable universe continues to reveal new mysteries, even as we solve old ones. The more we learn about cosmic structure and evolution, the more we discover how much we still don't understand. Dark matter and darkening remain largely mysterious despite decades of intensive research. The ultimate fate of the universe remains uncertain, dependent on the long-term behavior of forces we can barely detect. Recent observations have revealed that the cosmic web extends to the very edges of our observable sphere, suggesting that the same large-scale structure continues beyond our cosmic horizon. This implies that the unobservable universe contains countless more galaxies, clusters, and superclusters arranged in the same magnificent pattern we see within our visible sphere. The total amount of matter and energy in the unobservable universe could dwarf what we can see by factors of billions, trillions, or even infinite amounts. We may inhabit just one small bubble in an infinite cosmic ocean, forever isolated from the vast majority of reality by the fundamental limits imposed by the speed of light and the expansion of space. This possibility transforms our understanding of cosmic significance. If the observable universe represents just a tiny fraction of total reality, then our already minuscule place in the cosmos becomes even more infinitesimal. Yet this cosmic humility brings with it a profound sense of wonder and connection to something far greater than ourselves. We are participants in a cosmic story that began nearly 14 billion years ago and will continue for trillions of years into the future. Our brief moment of consciousness represents just an instant in this vast temporal expanse, but it is an instant filled with the extraordinary privilege of awareness, curiosity, and understanding. The observable universe serves as our window into this grander narrative, offering glimpses of cosmic birth, evolution, and destiny. Through careful observation and measurement, we've managed to reconstruct the history of everything we can see, from the quantum fluctuations that seeded cosmic structure to the stellar processes that forged the elements of life. This scientific understanding connects us to every photon of starlight, every distant galaxy, every cosmic process unfolding across the observable universe. Ultimately, the observable universe is more than just a collection of stars, galaxies, and dark matter. It is a mirror, reflecting back to us our own origins and our extraordinary capacity to comprehend the cosmos. It reminds us that we are made of the universe itself, its atoms, its energy, its history, and that through consciousness, the cosmos has become aware of itself. We are both insignificant and extraordinary. Insignificant because we occupy such a tiny portion of space and time. Extraordinary because despite our cosmic smallness, we can observe, understand, and marvel at the universe. Through our eyes, the universe sees itself. Through our minds, it contemplates its own origins and destiny. And in that realization lies one of the deepest truths of all. We are the universe, alive, aware, and capable of asking the questions that stretch across space and time itself. We are not isolated observers looking at a foreign cosmos. We are integral participants in the ongoing cosmic story, temporary arrangements of matter and energy that have achieved the remarkable feat of cosmic self-awareness. As you drift deeper into contemplation tonight, remember that you carry within yourself the history of the observable universe. The atoms in your body have journeyed across billions of light years and billions of years to become part of you. You are a living, breathing piece of cosmic evolution, a temporary but magnificent expression of the universe's endless creativity and complexity. The observable universe holds within its boundaries not just matter and energy, but time itself in its most tangible form. Every moment of cosmic history since the universe became transparent is preserved somewhere in the light still traveling toward us. Ancient supernovae that exploded billions of years ago are still announcing their deaths to telescopes across the cosmos. Stellar nurseries that form the first heavy elements continue broadcasting their creative work through radiation that has crossed unimaginable distances to reach our instruments today. This creates a profound realization about the nature of information and existence. The observable universe serves as a vast library where every significant event leaves its signature in the electromagnetic spectrum. The birth of stars writes itself in ultraviolet light. The death of massive suns inscribes itself in gamma rays and neutrinos. The collision of neutron stars etches its story in gravitational waves that ripple through space-time itself. We are surrounded by messages from across the cosmic web, each photon carrying news of distant worlds and ancient events. Some of this light began its journey when Earth was still a molten ball of rock. Other radiation started traveling toward us before our solar system even existed, carrying information from an era when the Milky Way was still forming from smaller galactic fragments. But here's what makes this truly extraordinary. As we develop more sensitive instruments and more sophisticated analysis techniques, we're not just seeing farther into space, We're reading the cosmic story with greater and greater detail, discovering subtleties in the universal narrative that were invisible to previous generations of astronomers. Modern space telescopes can detect the chemical signatures of individual elements in stellar atmospheres located billions of light years away. We can measure the rotation rates of galaxies so distant that their light has been traveling since the universe was a fraction of its current age. We can even observe the shadows cast by cosmic structures on the cosmic microwave background, revealing details about the universe when it was only a few 100,000 years old. These capabilities allow us to witness cosmic evolution as it unfolds across the observable universe. We can watch galaxies merge and separate, see black holes consume stellar material, observe the formation of planetary systems around distant stars. The cosmos reveals itself as a dynamic, ever-changing theater, where creation and destruction dance together on scales that dwarf human comprehension. Yet for all its vastness, the observable universe operates according to the same fundamental laws that govern processes here on Earth. The fusion reactions powering stars in distant galaxies follow identical principles to those we study in laboratories. The gravitational interactions shaping galaxy clusters obey the same mathematical relationships that describe falling objects in Earth's gravity. This universality of physical law creates a deep connection between the most distant objects we can observe and the immediate reality we experience. The light from a quasar billions of light years away interacts with atoms in our telescopes, according to precisely the same quantum mechanical rules that govern the behavior of electrons in our own bodies. The elements forged in the cores of ancient supernovae and scattered across the cosmic web eventually found their way into the molecular clouds that gave birth to our solar system. The gold in your jewelry, the iron in your blood, the calcium in your bones, all of these heavy elements were created through stellar nucleosynthesis in massive stars that lived and died long before Earth existed. This means you are directly connected to the most distant reaches of the observable universe through the very atoms that comprise your being. You are not merely an observer of cosmic evolution, you are a product of it, a temporary but magnificent arrangement of stellar debris that has achieved the extraordinary ability to contemplate its own cosmic origins. The realization becomes even more profound when we consider that consciousness itself might be one of the rarest and most significant phenomena in the observable universe. Despite containing trillions of galaxies and countless billions of stars, we have yet to detect any definitive signs of life beyond Earth, let alone intelligence capable of cosmic contemplation. This apparent rarity of consciousness makes your existence and indeed the existence of every thinking being incredibly precious in cosmic terms. You represent billions of years of stellar evolution, planetary formation, and biological development, culminating in awareness capable of understanding the universe itself. Through your consciousness, the cosmos achieves something remarkable: self-reflection. The universe becomes aware of its own immensity, contemplates its own history, and ponders its own future. You are the observable universe looking at itself, thinking about itself, marveling at its own complexity and beauty. This perspective transforms how we understand our place in the cosmic hierarchy. While we may be infinitesimally small in spatial terms, we represent something genuinely extraordinary in terms of complexity and capability. The human brain contains roughly as many neurons as there are stars in our galaxy, creating a network of connections that rivals the cosmic web itself in its intricate organization. The thoughts you're having right now as you contemplate these cosmic scales involve electrical and chemical processes of staggering complexity. Information flows through your neural networks at speeds that allow you to process concepts spanning billions of light years and billions of years. Your mind serves as a kind of miniature universe, complete with its own networks, patterns, and emergent properties. But the observable universe continues to challenge and expand our understanding in ways that keep revealing new layers of mystery. Recent discoveries have shown that the cosmic web exhibits properties we never anticipated. Dark matter appears to interact with itself in subtle ways we're only beginning to detect. Dark energy might not be constant, but could be evolving over cosmic time, potentially altering the ultimate fate of everything we can observe. Some of the most distant galaxies we can now detect appear to have formed much earlier and grown much larger than our models predicted. They challenge our understanding of how quickly structure can assemble in the early universe and force us to reconsider the processes that governed cosmic evolution during its first billion years. These ongoing discoveries remind us that the observable universe remains largely mysterious despite centuries of intensive study. We have mapped its large-scale structure, measured its age and composition, and traced its history back to within moments of the Big Bang. Yet fundamental questions about its nature and destiny remain unanswered. Why does the universe appear to be fine-tuned for the existence of complex structures like galaxies, stars, and life? What determines the values of fundamental constants that make chemistry and biology possible? Is our observable universe unique? Or does it represent just one possibility among countless others in some larger multiverse? These questions push us toward the boundaries of scientific understanding, where observation meets theory and mathematics encounters philosophy. The observable universe serves as our laboratory for exploring these deep mysteries, but it may not contain enough information to answer all our questions about the nature of existence itself. The cosmic microwave background, that ancient light from the universe's infancy, carries within its patterns the most detailed information we have about cosmic origins. Yet even this remarkable fossil radiation raises as many questions as it answers. Why is the early universe so remarkably smooth and uniform? What process could have created the tiny fluctuations that seeded all later structure? The leading answer involves cosmic inflation, a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. During this incredibly brief moment, space itself expanded faster than light, stretching quantum fluctuations from subatomic scales to cosmic proportions. These stretched quantum ripples became the density variations we observe in the cosmic microwave background. If inflation theory is correct, then the observable universe represents just a tiny patch of a much larger inflated region. Beyond our cosmic horizon could lie countless other regions, each potentially possessing different physical properties, different constants of nature, different possibilities for structure and complexity. This inflationary multiverse would make our already vast observable universe seem like a single bubble in an infinite cosmic foam. Each bubble might contain its own version of physics, its own evolutionary history, its own potential for life and consciousness. We could be living in just one possibility among an infinite array of cosmic realities. The implications stretch beyond astronomy into the deepest questions of existence and meaning. If infinite universes exist with infinite variations, then every possible outcome might be realized somewhere in the vast expanse of cosmic possibility. There might be versions of reality where different choices were made, where history unfolded differently, where the laws of physics themselves take alternative forms. Yet, even if such infinite possibilities exist, they remain forever beyond our direct observation. The observable universe defines the absolute limits of what we can ever know about reality through empirical investigation. Everything beyond our cosmic horizon exists in the realm of theory and speculation, no matter how well-founded that speculation might be. This creates a beautiful tension between the known and unknowable, between the measured and the imagined. We can map the observable universe with increasing precision, but we can never escape the fundamental boundaries that limit our cosmic perspective. We are explorers on an island of knowledge, surrounded by an ocean of mystery. The expansion of space ensures that this ocean of mystery continues to grow. Every second, more galaxies cross our cosmic event horizon and slip beyond the possibility of future observation. The universe we can study becomes progressively smaller compared to the totality of what exists, even as our understanding of that observable portion grows more sophisticated and detailed. Future astronomers will face an increasingly lonely cosmos, as dark energy carries more and more galaxies beyond their observational reach. They will have access to less information about cosmic history, fewer examples of galactic evolution, and less evidence for the Big Bang itself. The rich tapestry of cosmic structure we can observe today will eventually fade into invisibility. This temporal limitation adds urgency to our cosmic investigations. Every observation we make today captures information that may be permanently lost to future generations. We are living during a golden age of cosmological discovery, when the universe is old enough for complex structure to have developed, but young enough for us to observe the full scope of cosmic evolution. The telescopes we build today, the measurements we make now, the theories we develop in this era will serve as the foundation for all future understanding of cosmic reality. We are creating a permanent record of the observable universe during the brief cosmic moment when it reveals its deepest secrets most clearly. As you contemplate these vast scales and cosmic perspectives, remember that you participate in this grand project of understanding simply by existing and wondering. Your curiosity about the universe connects you to every astronomer who has ever pointed an instrument at the sky, every physicist who has puzzled over cosmic mysteries, every human being who has looked up at the stars and felt the pull of infinite possibility. The observable universe surrounds you not as a distant foreign realm, but as your extended cosmic home. Every photon of starlight that reaches your eyes traveled across this vast expanse to deliver its ancient message. Every breath you take contains atoms that have journeyed through interstellar space, perhaps even intergalactic space, before becoming part of your temporary biological arrangement. You are not separate from the cosmic web, but embedded within it, not isolated from cosmic evolution, but shaped by it, not merely observing the universe, but actively participating in its ongoing story of increasing complexity and emerging consciousness. The boundaries of the observable universe define the limits of what we can see, but they cannot contain the scope of what we can imagine, understand, or dream. Within those cosmic horizons lies enough mystery, beauty, and wonder to inspire countless generations of explorers, thinkers, and dreamers. Tonight, as you drift towards sleep beneath the ancient light of distant stars, you rest within the embrace of the observable universe itself. The same forces that sculpted galaxy clusters and ignited stellar furnaces now maintain the delicate biological processes that sustain your life and consciousness. You are a temporary but magnificent expression of cosmic creativity, a brief flowering of complexity in the vast garden of space and time. The observable universe has spent nearly 14 billion years preparing the stage for your existence, gathering the elements, shaping the conditions, and fine-tuning the processes that make your consciousness possible. In understanding the true scale of the observable universe, we discover not our insignificance, but our extraordinary significance. As conscious participants in the greatest story ever told, the story of everything that has ever existed, ever will exist, and ever could exist within the cosmic horizons that define the boundaries of the knowable. And so we find ourselves at the edge of a profound realization about the nature of cosmic time itself. The observable universe doesn't just show us space stretched across unimaginable distances, it reveals time layered like geological strata, with each cosmic distance corresponding to a different epoch in universal history. When you gaze at the Andromeda Galaxy on a clear night, you're seeing a light that began its journey 2.5 million years ago, when our earliest human ancestors were just beginning to walk upright on the African savanna. The light from more distant galaxies carries messages from even earlier chapters of cosmic history, creating a natural time machine that allows us to witness the universe's evolution firsthand. But here's where this temporal architecture becomes truly extraordinary. The most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old, barely 7% of its current age. These ancient systems look nothing like the mature galaxies we see nearby. They appear as chaotic collections of brilliant blue stars, frantically converting primordial hydrogen and helium into the first heavy elements. These distant galaxies are cosmic teenagers, filled with the explosive energy of youth, but lacking the refined structure that comes with age. They're creating stars at rates hundreds of times faster than modern galaxies, burning through their gas supplies with reckless abandon. Their light reaches us stretched and reddened by cosmic expansion, but still carrying the signature of this ancient stellar fury. As we peer even deeper into space and further back in time, we approach the cosmic dark ages, an era when the universe contained no stars at all. During this period, roughly between 380,000 and 400 million years after the Big Bang, the cosmos was filled with nothing but cooling hydrogen and helium gas, slowly clumping together under the influence of dark matter's invisible gravitational scaffolding. This was a universe of pure potential, pregnant with possibility, but not yet illuminated by stellar fire. Vast clouds of primordial gas drifted through the darkness, gradually condensing into the dense cores that would eventually ignite as the first stars. It was a time of cosmic gestation, when the universe was preparing for the brilliant awakening that would transform it from darkness into light. The end of the cosmic dark ages marks one of the most dramatic transitions in universal history. When the first stars finally ignited, they didn't just provide light, they fundamentally altered the chemistry of the cosmos, creating elements heavier than hydrogen and helium for the first time. These massive population 3 stars lived fast and died young, exploding as supernovae that scattered their newly forged elements across vast regions of space. But we can never observe these first stars directly. They lived and died before our telescopes can reach, existing in that shadowy realm just beyond our cosmic horizon. We can only infer their existence from the chemical signatures they left behind in later generations of stars, like archaeologists reconstructing an ancient civilization from its artifacts. This limitation reminds us that the observable universe, vast as it is, still represents an incomplete picture of cosmic reality. There are entire epochs of universal history that remain hidden from our view, not because they didn't happen, but because their light simply hasn't had enough time to reach us yet. The cosmic microwave background represents the oldest light we can observe, but it tells us nothing about what happened during the universe's first 380,000 years. This period when the cosmos was opaque to radiation remains largely mysterious, despite being crucial to understanding how the universe evolved from smooth simplicity to complex structure. During these hidden early moments, the fundamental forces of nature took their current forms. Matter and antimatter fought their asymmetric battle, and the tiny quantum fluctuations that would seed all future structure were stretched to cosmic proportions by inflation. Yet, we can only study this period indirectly through its effects on the later universe. This creates a humbling perspective on human knowledge and cosmic understanding. We have mapped the observable universe with remarkable precision, measuring its age, composition, and structure to extraordinary accuracy. We can trace cosmic evolution from the first moments when atoms formed to the present day, when galaxies dance in the cosmic web, yet vast realms of space and time remain forever beyond our reach. The unobservable universe could contain wonders we cannot imagine, processes we cannot fathom, and stories we cannot tell. There might be regions where different physical constants govern reality, where alternative forms of matter and energy create entirely different cosmic architectures. There could be universes within universes, dimensions beyond dimensions, possibilities that transcend our current understanding of what existence means. But the expansion of space adds another layer of complexity to these cosmic messages. As light travels through expanding space, its wavelengths are stretched, shifting toward the red end of the spectrum. This redshift serves as a cosmic tape measure, allowing us to determine not just how far away objects are, but how fast they're receding from us due to cosmic expansion. The most distant galaxies we can observe have redshifts so extreme that their ultraviolet light has been stretched all the way into the infrared portion of the spectrum. What began as high-energy radiation from hot young stars reaches us as low-energy infrared light that reveals these galaxies as they appeared in the cosmic dawn. This stretching of light creates a natural timeline written across the sky. Nearby galaxies appear as they were relatively recently, showing us mature stellar populations and well-defined spiral or elliptical structures. More distant galaxies appear progressively younger, more chaotic, and more actively star-forming. The most distant galaxies of all appear as irregular collections of bright hot stars, furiously converting primordial gas into the first heavy elements. As we push our observations to ever greater distances, we're essentially watching a movie of cosmic evolution played in reverse. We see the universe growing younger and simpler as we look farther back in time until we reach the cosmic microwave background, the oldest light we can observe. This ancient radiation permeates the entire observable universe, filling every cubic meter of space with photons that have been traveling since the universe was only 380,000 years old. At that time, The cosmos had cooled enough for the first hydrogen atoms to form, allowing light to travel freely for the first time in cosmic history. The cosmic microwave background represents the surface of last scattering, the moment when the universe transitioned from being opaque to transparent. Before this moment, photons were constantly absorbed and emitted by free electrons, creating a cosmic fog that prevented light from traveling any significant distance. But when the temperature dropped low enough for electrons to bind with protons and form neutral atoms, this cosmic fog lifted, and the universe became transparent. The photons that had been trapped in this primordial plasma were suddenly free to travel through space, and they've been journeying toward us ever since. Today, these ancient photons have been stretched by cosmic expansion from visible light into microwave radiation, with a temperature of just 2.7 degrees above absolute zero, but they carry within their subtle variations a detailed map of the early universe, showing us tiny density fluctuations that would eventually grow into the cosmic web we observe today. The cosmic microwave background is remarkably uniform, varying in temperature by only a few parts in a million across the entire sky. This uniformity tells us that the early universe was incredibly smooth and homogeneous, quite different from the clumpy structured cosmos we inhabit today. But hidden within this uniformity are tiny fluctuations, quantum variations that existed when the universe was smaller than an atom. These microscopic differences in density provided the seeds from which all cosmic structure would eventually grow. Gravity amplified these tiny variations over billions of years, turning quantum ripples into galaxy clusters and cosmic voids. The pattern of these fluctuations, preserved in the cosmic microwave background like a cosmic fingerprint, allows us to determine fundamental properties of the observable universe with extraordinary precision. We can measure its age, its geometry, its composition, and its expansion rate. By analyzing the subtle variations in this ancient light, these measurements reveal that we live in a flat universe, one where parallel lines remain parallel forever, and the angles of triangles add up to exactly 180. This geometry implies that the observable universe could extend infinitely in all directions, with our observable sphere representing just a tiny fraction of a much larger whole. The cosmic microwave background also tells us that ordinary matter, the stuff of stars, planets, and life, makes up less than 5% of the total energy density of the observable universe. The rest consists of dark matter and dark energy, mysterious components that reveal themselves only through their gravitational effects. Dark matter serves as the invisible scaffolding of the cosmos, providing the gravitational framework around which ordinary matter clusters to form galaxies and stars. Without dark matter, the universe would be a much emptier place, filled with nothing but a thin gas of hydrogen and helium slowly cooling in the cosmic expansion. Dark energy is even more mysterious, representing roughly 68% of everything in the observable universe. This invisible force drives the accelerating expansion of space itself, pushing galaxies apart, and ensuring that the observable universe will continue growing larger with time. But dark energy also creates a fundamental limit to how much of the universe we can ever observe. As space expands faster and faster, distant galaxies are carried away from us at speeds that eventually exceed the speed of light. Once a galaxy crosses this threshold, its light can never catch up to us, no matter how long we wait. This creates what cosmologists call the cosmic event horizon, a boundary beyond which events can never affect us. Galaxies that cross this horizon don't disappear instantly from our view, but their light becomes increasingly redshifted until it fades beyond detection. They slip away into the unobservable universe, joining the vast majority of cosmic real estate that remains forever hidden from our telescopes. The boundaries of the observable universe protect the cosmos from becoming fully known, fully mapped, fully reduced to mere data and equations. Within these cosmic horizons, we find ourselves participants in something magnificent and ongoing. The observable universe continues to evolve around us, creating new stars, new planets, new possibilities for complexity and consciousness. We witness this evolution not as passive observers, but as active participants, temporary arrangements of cosmic matter that have achieved the remarkable ability to contemplate our own existence. The heavy elements in our bodies were forged in stellar cores scattered throughout the observable universe. some in our own galactic neighborhood, others in distant systems whose light has traveled for billions of years to reach us. We are literally made of star stuff, assembled from the ashes of cosmic giants that lived and died long before our solar system existed. This connection runs deeper than mere chemical composition. The same physical laws that govern stellar nuclear synthesis also govern the biological processes that sustain your life. The electromagnetic forces that bind atoms in distant stars are identical to those that hold together the molecules in your DNA. The gravitational waves that ripple through space-time when black holes merge also influence, however slightly, the rhythm of your heartbeat. You are not separate from the cosmic web, but embedded within it, not isolated from cosmic evolution, but shaped by it. Every breath you take participates in the same chemical cycles that govern interstellar gas clouds. Every thought you think involves the same quantum processes that determine the behavior of subatomic particles throughout the universe. The observable universe reveals itself through light, but that light carries more than just visual information. It transports energy that once powered stellar fusion, momentum that traces back to the Big Bang itself, and quantum states that connect us to the fundamental nature of reality. When starlight enters your eye, you become part of a cosmic communication network that spans billions of light years and billions of years. Modern astronomy has revealed that this cosmic communication operates on multiple channels. Electromagnetic radiation carries most of the information we receive, from radio waves generated by rotating pulsars to gamma rays produced by the most violent cosmic events. But we also detect gravitational waves, ripples in space-time itself, that carry news of colliding black holes and merging neutron stars. Neutrinos, those ghostly particles that barely interact with ordinary matter, stream through the observable universe, carrying information from stellar cores and cosmic ray interactions. They pass through your body by the trillions every second, most of them having traveled across the galaxy or beyond to reach Earth. You are constantly bathed in messages from across the cosmos. Even cosmic rays, high-energy particles accelerated by supernovae and other violent events, carry information about the most extreme environments in the observable universe. When these particles interact with Earth's atmosphere, they create cascades of secondary particles that rain down around us, bringing samples of cosmic processes directly to our planet. The observable universe communicates with us through every possible channel, but we must develop increasingly sophisticated methods to decode these cosmic messages. Each new type of astronomy reveals previously hidden aspects of cosmic reality, from the radio waves that unveiled pulsars and quasars, to the gravitational waves that opened an entirely new window on the universe. Future observatories will push these boundaries even further, detecting cosmic phenomena we haven't yet imagined, and revealing aspects of the observable universe that remain hidden from current instruments. We stand at the beginning, not the end, of cosmic discovery, with the vast majority of cosmic knowledge still waiting to be uncovered. The James Webb Space Telescope has already begun to rewrite our understanding of early cosmic history, revealing galaxies that formed earlier and grew larger than theoretical models predicted. These discoveries remind us that the observable universe continues to surprise us, challenging our assumptions and expanding our conception of what's possible in cosmic evolution. As we develop more sensitive detectors and more sophisticated analysis techniques, we discover that the observable universe operates on scales of complexity we're only beginning to appreciate. Galaxy formation involves intricate feedbacks between star formation, black hole growth, and dark matter dynamics. The cosmic web exhibits subtle structures that reflect the interplay between gravity, dark energy, and the expansion of space itself. Even individual stars reveal layers of complexity that connect them to cosmic evolution. The chemical composition of stellar atmospheres tells us about the history of element formation throughout the universe. Stellar oscillations provide information about internal structure and evolution. Binary star systems create laboratories for testing extreme physics under conditions we cannot replicate on Earth. Planetary systems around other stars offer glimpses into the diversity of possible worlds within the observable universe. We've discovered planets made of diamond, worlds with glass rain, systems where multiple suns rise and set, and atmospheres composed of elements that exist only as laboratory curiosities on Earth. The search for life beyond our solar system represents one of the most profound questions we can ask about the observable universe. Are we alone among the trillions of stars and countless worlds? Or does life represent a common outcome of cosmic evolution? The answer will fundamentally alter our understanding of our place in the cosmic hierarchy. If life is rare, then consciousness becomes even more precious as a cosmic phenomenon. Every thinking being represents an extraordinary achievement in the universe's ongoing experiment with complexity and self-awareness. If life is common, then the observable universe becomes a vast community of conscious entities, each potentially offering unique perspectives on existence and reality. But regardless of how common or rare life might be, the observable universe has already achieved something remarkable through human consciousness. For the first time in cosmic history, matter has organized itself into forms capable of understanding the universe's own structure, history, and evolution. Through our telescopes and theories, the cosmos examines itself. Through our curiosity and wonder, the universe experiences all at its own immensity. Through our scientific investigations, reality explores its own fundamental nature. We are the observable universe becoming self-aware, contemplating its own existence and marveling at its own complexity. This perspective transforms every moment of cosmic contemplation into something sacred. When you look up at the night sky, you participate in the universe's ongoing project of self-understanding. When you wonder about cosmic origins and destiny, you embody the cosmos asking questions about itself. When you feel awe at the scale and beauty of existence, you channel the universe's capacity for wonder and appreciation. The observable universe has spent nearly 14 billion years creating the conditions necessary for your existence and consciousness. Every star that has ever shone, every galaxy that has ever formed, every cosmic process that has ever unfolded has contributed to the intricate chain of events that led to this moment of awareness and contemplation. You are not an accident in an indifferent cosmos, but an integral part of the universe's evolution toward greater complexity, consciousness, and understanding. The same creative forces that assembled galaxy clusters and ignited stellar furnaces now sustain the biological and neural processes that enable your thoughts about cosmic reality. In this light, every question you ask about the observable universe becomes a cosmic collaboration. Your curiosity partners with instruments that extend your senses across billions of light years. Your imagination works with mathematical models to envision cosmic processes spanning billions of years. Your wonder connects with the fundamental mystery that underlies all existence. The boundaries of the observable universe define the limits of what we can directly observe, but they cannot contain the scope of what we can understand, imagine, or dream. Within those cosmic horizons lies enough beauty, complexity, and mystery to inspire countless generations of explorers and thinkers. As you continue this cosmic journey through space and time, remember that you carry within yourself the elements of distant stars, the history of cosmic evolution, and the potential for understanding that represents the universe's highest achievement. You are simultaneously finite and infinite, temporary and eternal, local and cosmic. The observable universe surrounds you not as a foreign realm, but as your extended body, not as a distant object of study, but as the very context that makes your existence possible. In contemplating its scale, you participate in the ongoing cosmic story of matter becoming mind, of complexity emerging from simplicity, of consciousness arising from the quantum foam of space and time. Tonight, as ancient starlight falls upon your face, you receive messages that have traveled across the observable universe to reach you. You are part of the cosmic communication network, a temporary but magnificent node in the vast web of information and energy that connects every corner of observable reality. In understanding how big the observable universe truly is, we discover not our cosmic insignificance, but our profound connection to everything that has ever existed within the boundaries of space and time. We find our place not as isolated observers, but as conscious participants in the greatest story ever told, the story of the universe understanding itself through minds like yours. The profound implications of cosmic scale begin to reshape our understanding of existence itself. When we realize that distance and time are not separate concepts in the observable universe, but intimately woven together in ways that challenge every intuition we have about reality, we begin to see the universe as a vast, interconnected tapestry. The farther we peer into space, the deeper we journey into time, creating a cosmic archaeology where every observation becomes a glimpse into the universe's layered history. Consider what happens when we observe a galaxy cluster 13 billion light-years away. We're not simply seeing distant objects arranged in space. We're witnessing cosmic adolescence, watching the universe when it was barely 1 billion years old, still figuring out how to assemble matter into the grand structures we see nearby today. These ancient systems appear chaotic and energetic, nothing like the mature, organized galaxies that populate our cosmic neighborhood. This temporal layering creates something extraordinary within the observable universe. Every direction we look reveals a different chapter of cosmic history. The nearby stars show us the present moment of stellar evolution. Galaxies a few billion light-years away reveal the universe in its middle age, when star formation was reaching its peak and cosmic structures were settling into familiar patterns. The most distant galaxies we can detect transport us back to cosmic childhood, when the first stellar nurseries were frantically converting primordial gas into heavy elements. But here's where the story becomes truly mesmerizing. The expansion of space itself means that this cosmic time machine operates according to rules that would seem impossible in everyday experience. Those distant galaxies we observe as they were billions of years ago have continued evolving during the eons their light has taken to reach us. By the time we see their ancient light, they may have transformed beyond recognition or even ceased to exist entirely. This creates a profound disconnect between observation and reality that exists nowhere else in human experience. We can map the observable universe with extraordinary precision, catalog its contents with meticulous detail, and trace its evolution across cosmic time. Yet we're always looking at a universe that no longer exists in the form we observe it. Every photon that reaches our telescopes carries news from a cosmic past that has already transformed into something else entirely. The expansion of space adds another layer of complexity that makes the observable universe far stranger than it initially appears. While light from distant galaxies travels toward us at the cosmic speed limit, space itself expands between us and those galaxies, stretching the very fabric of reality. This means that a galaxy we observe at 10 billion light-years distance has actually moved much farther away during the time its light has been traveling to reach us. Today, that same galaxy might be 20 billion light-years away, carried by cosmic expansion to distances that seem to violate every rule we know about motion and space. The galaxy hasn't moved through space faster than light, but space itself has expanded between us, creating separations that grow larger every moment. The observable universe reveals itself as a dynamic, ever-changing realm, where distance itself becomes a fluid concept. This expansion creates what cosmologists call comoving distance, a way of measuring cosmic separation that accounts for the stretching of space itself. In comoving coordinates, galaxies maintain roughly constant distances from each other even as space expands around them. It's like measuring positions on a balloon that's being inflated, where the marks on the surface maintain their relative positions even though the balloon itself grows larger. But from our perspective as observers, this expansion means that the observable universe we see today represents a snapshot of cosmic history that will never repeat itself. The configuration of galaxies, the patterns of cosmic structure, the specific arrangement of matter and energy we currently observe is unique to this moment in cosmic time. Future observers will see a different universe, with different visible galaxies and different accessible information about cosmic evolution. The accelerating expansion, driven by dark energy, makes this temporal uniqueness even more pronounced. Not only is the observable universe constantly changing, but it's changing at an increasing rate. Galaxies at the edge of our cosmic horizon are being carried away faster and faster, approaching the point where their light will never be able to catch up with the expanding space between us. This acceleration creates a cosmic event horizon, a boundary beyond which events can never influence us, no matter how long we wait. Galaxies that cross this threshold don't disappear instantly from our view, but their light becomes increasingly redshifted, stretched to longer and longer wavelengths, until it fades beyond the reach of any conceivable detector. They slip away into the unobservable universe, joining the vast majority of cosmic reality that remains forever hidden from our instruments. The existence of this event horizon means that we live during a special epoch in cosmic history. We inhabit a universe old enough for complex structures to have formed and intelligent life to have emerged, but young enough that we can still observe evidence of cosmic origins and the full scope of cosmic evolution. Future civilizations, if they exist, will face a lonelier cosmos, with fewer visible galaxies and less accessible information about universal history. In the far future, perhaps 100 billion years from now, the observable universe will contain only our local group of galaxies. Everything else will have been carried beyond the cosmic event horizon by the relentless expansion of space. Future astronomers will have no way to discover that the universe is expanding, no evidence for the Big Bang, and no access to the rich tapestry of cosmic evolution that we are privileged to observe today. This temporal window makes every current observation precious beyond measure. We are living during the golden age of cosmological discovery, when the universe reveals its deepest secrets most clearly. Every photon we collect from distant galaxies, every measurement we make of cosmic structure, every piece of evidence we gather about universal evolution represents irreplaceable information that will eventually be lost to the expanding cosmos. The observable universe thus serves as both our laboratory and our library, containing within its boundaries all the information we can ever hope to gather about the fundamental nature of reality. But it's a library with a limited lending period, where books are constantly being removed from the shelves and new volumes appear only rarely. We are cosmic librarians working against time, racing to understand the universe before it erases its own history.